Imagine that an ordinary sheet of aluminum costing about $25 is lying on your roof. No compressor is connected to it. There is no refrigerant inside. It makes no noise, does not rotate, and consumes almost no electricity. But on a clear night, its surface becomes colder than the surrounding air. And with the right coating, it can continue releasing heat even when the sun is shining above the roof. This is not a solar panel. It does not receive energy from light. It does almost the opposite. It sends heat from Earth into the cold of outer space. The technology is called passive radiative sky cooling. And the most surprising thing is not that it works. The most surprising thing is how simple a device using this effect can be. But before buying aluminum and white paint, you need to understand one important detail. An ordinary light-colored sheet on the roof and a true radiative cooler are not the same thing. One simply reflects part of the sunlight. The other must simultaneously reflect the sun and release its own heat very efficiently within a strictly defined range. This is what determines whether you get cooling or merely an expensive piece of metal. First, let us look at what it is working against. An ordinary window air conditioner can consume hundreds of watts, while a large unit can consume more than 1,000. On a hot day, the compressor turns on again and again, moving heat from inside the house to the outside. If the house is poorly insulated, the attic is scorching hot, and the roof absorbs sunlight all day, the system is not only fighting hot air, it is fighting heated walls, the ceiling, furniture, and the structure of the building itself. This is why off-grid cooling is especially expensive. And buying an air conditioner is not enough. You need solar panels, an inverter, and batteries capable of handling the evening load. And the more energy you spend removing heat, the more equipment you have to buy just to push that heat outside again. And now, the main question. Can the roof get rid of some of the heat on its own before the compressor turns on? To understand the answer, think of a cup of hot coffee. Even if you do not blow on it or put it in the refrigerator, it gradually cools down. Some of the heat goes into the surrounding air, but some leaves the surface in the form of invisible infrared radiation. The same thing happens with your skin, the ground, walls, and the roof. Any warm object constantly emits energy. Normally, the atmosphere absorbs a significant portion of this infrared radiation. Water vapor, carbon dioxide, and other molecules trap heat and return part of the energy back to the surface. But the atmosphere has a special transparent range, approximately from 8 to 13 micrometers. Radiation within this range passes through the air more easily and escapes upward. And above the atmosphere is an enormous thermal reservoir with a temperature of about -454 degrees Fahrenheit. Deep space. Therefore, a surface that emits well specifically within the atmospheric window and is protected from unnecessary heating can release more energy than it receives back. Its temperature begins to drop below the air temperature. This is why frost sometimes appears on a car or grass on clear nights, even when an ordinary thermometer reads slightly above the freezing point. The surface sees the cold sky and loses heat faster than the surrounding air can return it. But an obvious objection arises here. There is no sun at night. During the day, however, an enormous flow of solar energy strikes every part of the roof. Would that not destroy the entire effect? For a long time, that is exactly what happened. Nighttime radiative coolers had been known for a long time, but under direct sunlight, the surface heated up faster than it could release heat. The breakthrough came when researchers learned to separate two types of radiation. Sunlight arrives mainly in the shortwave range. Heat from the surface leaves in the long-wave infrared range. This means that a material can be designed to reflect almost all sunlight while simultaneously remaining a strong infrared emitter. In 2014, researchers at Stanford University demonstrated a multi-layer surface that cooled to almost 9 degrees Fahrenheit below the surrounding air under direct sunlight. It reflected approximately 97% of the incoming sunlight and released heat through the atmospheric window. There was no compressor. There was no refrigerant. Only the optics of the surface and an open view of the sky were at work. And this is where the story becomes truly interesting. The first prototype was a complex photonic structure. For an ordinary home, that sounds impractical. But the study proved the main point. Daytime cooling below the air temperature is physically possible. After that, other teams began searching for coatings, films, and porous materials that could be produced more cheaply and over larger areas. In 2017, researchers demonstrated a hybrid film made from polymer and microscopic glass particles. It also reflected sunlight and emitted heat within the required infrared range. Porous white coatings, special paints, roofing membranes, and panels with water channels appeared. In other words, the idea began moving out of the laboratory and onto the roofs of real buildings. But do not imagine that one sheet measuring 4 by 8 feet will replace central air conditioning. This is the first limitation that many videos do not mention. A radiative panel does not create an unlimited amount of cold. It removes heat at a certain rate, which depends on the coating, temperature, humidity, wind, cloud cover, and the amount of open sky. Under good conditions, this may amount to tens of watts of cooling from each square meter of surface. A 5A panel measuring 4 by 8 feet can remove a noticeable amount of heat, but the heat entering a typical American home in summer is measured in thousands of watts. It is more accurate to use radiative cooling as the first free stage of the system. A rooftop panel can cool water flowing through it. This water then enters a small heat exchanger, a storage tank, or the existing cooling system. As a result, the compressor receives already pre-cooled fluid and performs less work. Another option is to use the radiative surface to cool the roof and attic space, reducing the amount of heat that enters the house in the first place. And now we have reached the practical part. What would a simplified experimental panel look like? The base is a flat aluminum sheet. Aluminum is lightweight, conducts heat well, and quickly distributes it across the entire surface. Next, it needs a coating with two properties: very high reflectivity under sunlight and high emissivity in the thermal infrared range. This is why simply painting the sheet with any white paint is not enough. Some white coatings reflect visible light well but absorb near-infrared solar radiation. To the eye, they look the same, but on the roof they perform completely differently. For a real project, it is better to use a coating for which the manufacturer specifies solar reflectance and thermal emissivity, or a material specifically designed for cool roofs and radiative cooling. A layer of rigid insulation is needed beneath the aluminum. Without it, the cold panel will begin pulling heat from the scorching roof below, and a significant part of its capacity will be lost. It is also advisable to insulate the edges, because thin metal quickly absorbs heat from the mounts and frame. If you want to cool water, a copper or aluminum tube shaped like a long serpentine loop can be thermally attached to the back of the sheet. A small pump will slowly circulate water through the panel. But even here, it is important not to rush. The faster the flow, the less time the water has to cool during a single pass. The slower the flow, the colder the water can come out, but the lower the total volume of cooled water. The setting depends on the panel area and your heat exchanger. A screen that is transparent to thermal infrared radiation is sometimes installed above the surface to reduce heating from hot air and wind. But an ordinary sheet of plastic can ruin the system if it absorbs radiation in the 8 to 13 micrometer range. Therefore, the screen cannot be selected solely by how clearly you can see through it. And there is one more condition that can destroy the result, even with a properly assembled panel. It needs an open view of the sky. If it is placed under a tree, a canopy, or next to a hot wall, it exchanges heat not with the cold sky, but with the warm objects around it. The more sky the surface can see, the better. Now about climate. In a dry and clear place like Arizona, the potential is higher. Humid air contains more water vapor, which absorbs infrared radiation more strongly. Low, dense clouds also block the atmospheric window and return heat downward. Therefore, the same panel may show a good result on a dry desert night and barely drop below the air temperature in a humid coastal city. During the day, the task becomes even more difficult. If the coating absorbs even a few extra % of solar energy, this heating can cancel out the entire useful effect. Dust, dirt, and surface aging also change reflectivity. This means that the promise of install it once and forget about it forever sounds attractive. But in a real system, the surface will need to be inspected and cleaned. And yet, the idea remains remarkably powerful. Most cooling technologies first buy electricity, then use it to drive a motor, compress refrigerant, and only after that transfer heat outside. A radiative panel starts with a different question. Why spend electricity on all the heat if some of it can be sent directly into the sky? It will not replace air conditioning in every climate. It will not charge a battery. One cheap sheet will not cool an entire house. But a properly designed rooftop area can lower the surface temperature, pre-cool water, and reduce the load on a conventional system, day and night, without a compressor on the panel itself. And perhaps this is exactly how we should look at the future of the off-grid home. Not by searching for one magical machine that solves everything, but by combining several simple physical effects: good insulation, shading, nighttime ventilation, thermal mass, and a surface capable of releasing heat into space. Because the coldest object available to your home is not located in the basement and is not sold in a store. It hangs directly above the roof every night. 71. The only question is whether you can open the right window to it. If such a system could reduce the operation of your air conditioner by even a few hours a day, would you dedicate part of your roof to radiative panels? Write in the comments. And subscribe, because in the next video we will examine another technology that stores coolness without a huge battery and releases it into the house exactly when electricity is most expensive.